Today on Trigonometries, we're going to take a look at two examples about integration by parts. Now the formula for integration by parts is this here. The integral of u dv equals uv minus the integral of d du, where dv is v prime of x dx and du is u prime of x dx. The purpose of integration by parts is to try to reverse the product rule. And you can certainly use this formula to apply it directly, but there's actually an alternative algorithm that can help make this a little bit quicker and a little bit easier. And that's called the tabular method for integration by parts. We're going to do two examples today in order to see how the tabular method works. In our first example, we're going to compute the integral of x cubed sine of x dx. One type of problem where this method particularly shines is when you have an integral whose integrand is a product of a polynomial and another function that's relatively easy to take the antiderivative of. In this case here, sine of x is really easy to take antiderivatives of, and x cubed is a polynomial. The reason why polynomials are nice in this is because we're going to take a bunch of derivatives of one of these terms and a bunch of antiderivatives of the other. If you take derivatives of polynomials, eventually they go to zero. And so it always terminates the process sort of naturally. So what we need to do on a problem like this is we have two functions in the integrand that are multiplying together. We need to identify one of them to be our u function that we're going to differentiate and the other one to be our dv function that we're going to antidifferentiate. In this case, we'll pick the polynomial to be the u function and differentiate it, and the sine of x to be the dv function that we're going to antidifferentiate. On the polynomial side, let's go ahead and take all the derivatives. The derivative of x cubed is 3x squared, the derivative of 3x squared is 6x, the next derivative is 6, and the last derivative is 0 because the derivative of any constant is 0. On the antiderivative side, the antiderivative of sine of x is negative cosine of x, and the antiderivative of negative cosine of x is negative sine of x, and the antiderivative of negative sine of x is cosine of x, and finally the antiderivative of cosine of x is sine of x. To apply the integration by parts method using this table, we're going to draw an arrow from the first function in the derivative column, the x cubed, to the second function in the antiderivative column, the negative cosine of x. This arrow is going to indicate that we're going to multiply these two guys together. Then we go to the next layer and we draw an arrow from the 3x squared, which is the second function on the derivative side, to the sine of x, which is the third function on the antiderivative side. And we keep doing this all the way down until we run out of functions. Each of those arrows is going to indicate that we are going to multiply those functions together, and then we're going to add them in a certain way. But there's one additional piece. If you remember in the integration by parts formula, on the right-hand side, the uv is positive, but the integral is negative. And so this causes a sign change each time you go through these products. And so as a result, the first arrow here is going to have a positive sign, the second arrow will have a minus, the third arrow will have a positive, and it'll just continue to rotate like that. So now you have each arrow is telling you which products to make, and the signs on the arrow tell you whether to add or subtract them. Putting it all together, what this tells us is that the integral of x cubed sine of x dx is equal to the product of negative cosine of x and x cubed times a positive sign, which would just give us negative x cubed times the cosine of x. Then on the next one, we have a product of 3x squared and negative sine x, but times a negative number. And so we get plus 3x squared sine of x. And then we get plus 6x cosine of x, and then finally minus 6 sine of x. Because we're taking an indefinite integral here, we have to remember to add the plus c at the very end because this is the antiderivative only up to a constant. And that's how you use the tabular method in order to do the integration by parts. It's particularly useful when you have to chain multiple applications of integration by parts in order to get the answer. And you can certainly see that it works great if one of the functions disintegrates. But what happens if it doesn't? Is there a way to stop this process partway through if the derivative side doesn't eventually go to zero? And that's where our second example comes into play. In our second example here, we're going to compute the integral of e to the 2x times the cosine of x dx. Again, we need to pick a u function that we're going to differentiate and a dv function that we're going to antidifferentiate. In this case, it kind of almost doesn't really matter which one you do, but just to make the derivatives sort of easier, we'll do the derivatives as e to the 2x, and we'll do antiderivatives on the cosine of x. On the derivative side, let's take a couple of derivatives and sort of see what happens. Taking two derivatives of e to the 2x, we get 2e to the 2x, and then followed by another derivative of 4e to the 2x. Remember, you're going to have to use the chain rule here to get those derivatives. Taking the same number of antiderivatives on the antiderivative column, the antiderivative of cosine of x is sine of x, and the antiderivative of sine of x is negative cosine of x. Now, you probably noticed that if we just keep doing this process, we're just going to keep getting multiples of e to the 2x, and we're going to cycle through cosines and sines over and over again. So this is an example of a time where doing the tabular method just straight through isn't going to work because it's not going to terminate. So we need to have a way of sort of exiting the table at some point. Now we can apply the arrows like we did on the previous example to get the first few parts of the integration by parts, putting an arrow from e to the 2x to sine of x, and then an arrow from 2e to the 2x to negative cosine of x. And then we put the sign changes on them, plus and negative. Each of those arrows corresponds to an application of the integration by parts formula. But if you remember, the integration by parts formula is the integral of u dv equals uv times the integral of v du. And so the integration by parts formula, when you apply it, has another integral in it. So in order to exit here, we have to introduce that integral again. And the integrand of that integral is going to be a product of a derivative and an antiderivative that are on the same layer in the table, just like the original integral was on the first layer of this table. And so here, we're going to exit the process by drawing an arrow from 4e to the 2x to negative cosine of x, because they are on the same layer of this table. The sign change still follows, so you still get a plus, minus, and then here we get a plus for this arrow. But this product, this horizontal arrow, is now a product that's going to be inside of an integral. And so this would result in the integral of e to the 2x cosine of x dx being equal to positive e to the 2x times the sine of x plus, because we have a double negative, 2e to the 2x cosine of x minus the integral of 4e to the 2x times the cosine of x dx. Notice how the horizontal arrow produced a product that was still inside of an integral. And so this actually represents two applications of the integration by parts formula, and we exited with still having an integral here. But in this particular example, if you notice, the reason why this is going to work is that the resulting integrand in the second integral there looks a lot like the original integrand. It still has an e to the 2x and a cosine of x, it just has a different constant in front of it. So rewriting it, we get this here, and what we're going to do is we're going to add the integral that's 4e to the 2x cosine of x dx to the other side, because that's just 4 copies of the original integral. And when we do that, we end up with 5 times the original integral of e to the 2x cosine of x dx, and that'll be equal to e to the 2x sine of x plus 2e to the 2x cosine of x, which were the first two terms that we had. I've also added the plus c here because all of these equalities, since they have indefinite integrals, are always just true up to a constant. And so that constant on the right is telling you that you could potentially still have that constant there, just like you normally would for any kind of indefinite integral. Dividing by 5 and redefining the constant c, we end up getting the result of the indefinite integral of e to the 2x cosine of x dx, which will simply be equal to 1/5 e to the 2x sine of x plus 2/5 e to the 2x cosine of x, just 1/5 of what we had before, plus some constant c. And that's how you solve some integration by parts using the tabular method. You can use this as a tool to apply the integration by parts formula multiple times and eventually just get through it without having to do the formula each time. Or if you want, you can also use this to apply the integration by parts formula as many times as you want and then exit appropriately following these two examples. If you found this video helpful, go ahead and give it a like, and please subscribe to Trigonometry so we can give you some help on your homework later on. And we'll catch you next time on Trigonometry.